Hi everyone, I'm Luca. I work at INFN in Frascati, and today I will show you the moonlight cube for lunar laser ranging that will fly on one of the next lunar mission, in fact, in 2025. INFN and ASI and ESA somehow paid the bills of what you are seeing now. So let's start from the end. This is a nice picture of our space qualified, accepted for flight, proto-flight model that includes the moonlight cube on the left, which is a next generation cube for lunar laser ranging unaffected by lunar librations. And also the double gimbal, the MPEG hardware that will finally tune the front face of the cube with respect to the Earth after landing on the near side of the moon once and forever, so that the front face of the cube will face Earth in order to exploit the lunar laser ranging technique. Why it is advisable to put mirrors on the moon? Well, for the interest of INFN and in general for basic physics, basic science, you are gonna laser range the moon in order to track its orbit and eventually compare it, match or mismatch it with respect to the prediction. That is a way to test general theory of motions in the Earth, Moon, Sun system. It's an effective way, and in fact is cheap. And the trick is the use of these special mirrors that are not mirrors. They come in the shape of corner of cubes, and they bounce back the incoming light front to the emitter, and they are very useful for that. This kind of hardware is already on the moon from the 60s and 70s. They were left on the moon by the Americans on board Apollo missions 11, 14, and 15, and also on board on Soviet Russians rovers. As you may see from the pictures, the shape and geometry and the mechanical details is very different from the hardware that we will fly in 2025, especially if you have a look at the left arrays that are wide arrays that are at least 1 square meter wide, and they are covered with at least 100 cubes, which have got a front face diameter of 1.5 inches each. The Apollo 15 tray is even bigger, is about a couple of square meters wide, and has got 300 small cubes. Now, given the arrays, given the arrays that are on the moon at the moment, it is not possible to measure the time of flights to the arrays and back, and then extract the distance to the moon to a level of accuracy and precision, which is at the moment down to one centimeter, but it is not possible to go better. So if you put together all the laser ranging data, or a good subset of them from the 70s until a couple of years ago, you may see that you are limited to the 1 centimeter level accuracy. And this is due to the very geometry of the actual arrays on the moon that are wide enough to sense the libration cycle and to be sensed, not sensed as point-like target anymore through the lunar laser ranging technique. And also there is another aberrational effect, which is due to the multi-scatterer, the reflection geometry. So basically, the retroreflected beam is expanded artificially because it's a convolution of the single reflection of the at least 100 mirrors. So even after data analysis and data polishing and data modeling and tricking, it's not possible to go better than the 1 centimeter level. In principle, with the second generation cubes that are single bigger cubes, it will be possible to keep intact, to save the pulse width, the pulse length in time, and then lower the accuracy and precision of the distance to the moon down to 1 millimeter or better. So the take-home message is that we want to move from a single tray multi-CCR wide geometry to a single cube, bigger cube. It's 10 centimeter across, the big one on the right, and they may be eventually scattered all over the near face of the moon. That is when we were awarded in 2019, in fact, at the European Lunar Symposium in Manchester, 5 years ago from now, the commissioning of the hardware. So we started since then, after summer in 2019, all the machinery and bureaucracy to get through all the phases of design and development and manufacturing and testing of the hardware, getting through the different model phases. We even took dead ends. It happened, given also the unprecedented times we lived in. And finally, let's say by the end of 2022, yes, we got to the final stage of designing, and we were ready to get into production to get the hardware test. And the flight of Moonlight and MPEG will be on board the IM-3 Nova-C lander, IM-3 mission Nova-C lander, heading towards the Rainer Gamma swirl in 2025. Here is another picture which shows you the extent of the azimuth and elevation spans of the mechanism that will help greedily aligning the front face of the cube with respect to the Earth. And finally, so we were accepted for flight basically at the end of last year, and since the end of 2023, we are in storage and waiting for our lift to the moon. Now, that was what I wanted to tell you about the hardware. Concerning the science, so there are three pillars that enable the science of Moonlight. First of all, the big cubes on the moon. Second, the Lunar Laser Engine Station on Earth, like Apollo in New Mexico, Grasse in France, Madeira in Italy, which is also operated by the Italian Space Agency. Third, the planetary and orbital integrator, which is also able to digest the lunar laser engine data and compare them and compare the measured track of the moon with the predictions of the theory, of course. The scientific goals, we have got primary scientific goals, let's say, at least for me, for INFN, which which relates to the test of theory of motion in the Earth-Moon-Sun system, where the relative pulls of gravity are at work. And secondary goals, again, secondary for me, for my point of view, is the use of lunar laser ranging data, as it's been done already with the actual hardware, in order to test for geodesy and geology of the moon. That is a nice table. It's just a summary of the claim of the measurements that can be done if we are able to lower, and we will able to lower the accuracy on the measurements of the distance of the moon, thanks to the new cubes, once they will be set in place, and after several years, I would say, of data integration and analysis. And they are just a number of parameters that characterize the general theory of relativity. And in summary, so a big single CCR payload, which will be active, and the double gimbal and pack will help fine-tune the front face of the cube towards the Earth. It's a 50-year lifetime experiment in principle and more, and it will help to use the moon as a test bed for science. Now, if the organizer forgive me, I will give you also a hint of our talk for next year, if we are going to be awarded out of it. But this is really for next year. It's just a drill. It's the end.
Hi, thanks. Yeah, is the pointing just done once at the start of the mission, or do you adjust the pointing depending on which laser station's using you?
It will be done once only after landing, and then the motor will get stuck and stay there for a while.
Hi, Jacopo Tessino, Grand Sasso Science Institute. So you mentioned two aspects that are kind of new with respect to the Apollo retroreflectors, one of which is size, fewer, bigger reflectors, and the other is the pointing. So what is the magnitude, let's say, of the contribution of these two things to reaching millimeter level? Could you do one and not the other, or like, yeah?
Okay, I see. No, you couldn't, because you need a big cube to like a big mirror if you want to see it farther away. On the other hand, you want to have just one big, because you want to get rid of the extended geometry. So big cube, single.
A simple question. How close to the horizon does the ray from your sight to the Earth?
How close to the horizon?
Yeah, what's the elevation of the ray above the surface? Because you have topography to worry about.
Yes, but I mean, on the moon, the cube will land. Now I cannot remember. I cannot remember the coordinates of the landing site, but it's close enough to the equator. So basically, the cube will face the zenith of the local landing site, and I'm not sure if I'm answering your question.
Okay, never mind. Thank you.